Okay, number 11, which of the following scenarios where a ball is described, the motion of the ball is described as balanced? Balance we know that there is no change in motion if it is balanced. It's not changing its speed or its velocity. A ball rolling down the ramp would be increasing speed because of the acceleration due to gravity. So it would be accelerating, which means it would be speeding up as it rolls down the ramp. So that would not be a true statement. A ball rolling across the floor at a constant speed. The word constant means no change. So this one is probably one of our choices. 3, a ball falling from the top of a building. Again, falling, that means it's going to be accelerating due to the force of gravity is going to be accelerating it down, which means it would be changing its speed. So this one is going to be unbalanced as well. A ball on a rope rocking back and forth. When it's rocking back and forth, it's changing its direction, which means that it is not balanced. It is changing. Sorry, not balanced. And so 5, a ball spinning in place on a frictionless surface. Friction means that it's not slowing down at all. So it's going to be remaining a constant speed as well. So that one would also be balanced. Letter A, 2 and 5. We checked 2, we checked 5. Letter B, 2, 4, and 5. 4 was not balanced because it was rocking back and forth, changing direction. 1, 2, and 5. 1 was not balanced because it was rolling down a ramp, which means it was accelerating, getting faster as it got closer to the bottom. And 1 is incorrect, so is 3 and 4. Actually, those are all changing. So the only correct answer is A.
Okay, number 12. The table below shows the results of the student investigation. So I'm looking at this and I see distance and I see speed. So let's see. Just by looking at this, my distance is getting bigger by like 200 meters each time, and it's getting faster. So it's getting faster as it's going down there. Okay, so which of the following statements best explains the data collected by the students shown in the above table? The speed of the toy car increases due to forces greater than gravity. Okay, so gravity is constant, and we don't really know why these are, we do know that it's getting faster, but we really don't know why. The speed of the toy car decreases due to balance forces. Well, if it were balanced, then it would be a no change in speed, and so because balance means no change in the motion, so it wouldn't be decreasing if it's not changing, so that's wrong. The speed of the toy car increases due to balance forces. Well, we do know that unbalanced forces, cause a change in motion. So we do like that. It is, that one, the speed of the toy car decreases due to friction. Well, that could be true, but friction is considered an unbalanced force. So this is the better answer. I like this one too, but this one is the best answer due to unbalanced forces. Number 13. So we've got speed, velocity, and acceleration on the table, and it looks like just kind of characteristics of each. So speed shows how fast an object is traveling. That is true, and velocity includes the speed of an object. We also know that it also has something about direction. Velocity needs to have a direction as well. Acceleration is a change in the direction of an object. Yeah, so let's see what this is here. Which of the following would be found in the part labeled Y? Okay, so we're looking for this one right here. So it shows the direction in which the object is traveling? No, this is velocity. That would not be under acceleration. Shows how fast an object is traveling? Maybe, but that's more speed. That is how fast an object is traveling. Exactly. Shows a change in the speed of an object. I like this because acceleration is a change in velocity. And if we know that velocity is both speed and direction, it could be either or. So I like this one. Shows the time it takes an object to travel a distance. Again, that is speed. The correct answer here is going to be C. And number 14, Deep Space One was a spacecraft powered by an engine that gave off xenon particles to change velocity. So xenon is part of is an element to change velocity. So we're changing either speed or direction. So they use xenon to change speed or direction. It had a mass of 500 kilograms. So this is important. Which expression can be used to find the spacecraft's acceleration? So we're looking for this. If its engine created a net force of 0.1 newtons. Okay, so I know that we use the formula force equals mass times acceleration, and we put it in the triangle like this, and we're looking for acceleration. So if we cross out acceleration, because that's what is in the dark, we don't know. What is left is this formula. So let's just plug in what we know. We know the force is 0.10 divided by our mass, which is 500 kilograms. Make sure you know your thing. And then which one of this matches it? Well, it is this one. This one would be this is times, and we know we're not doing times. This one over here is flipped, so that one is wrong, and this one is add, which there's no addition in this formula. Number 15, you are riding in a vehicle with a coffee cup on the dashboard while traveling 30 kilometers per hour. So I've got a coffee cup on the dashboard, not a good idea, traveling 30 kilometers per hour. The vehicle suddenly makes a sudden stop. Here is my unbalanced horse to avoid hitting the car that has stopped in front of it. So, just like Newton's law says over here, that its law of inertia states that an object in motion will stay in motion at the same speed and direction unless an unbalanced force acts upon it. So if we are going 30 kilometers per hour, everything in that car, including that coffee cup, is going 30 kilometers per hour. If we apply the brakes to the car will stop. That is the unbalanced force. However, the coffee cup is not a part of the car, so it will continue to go in the same direction and same speed, which is forward, at 30 kilometers per hour until something stops it, probably the windshield. So you're moving and you're going in a forward direction. It doesn't say anything about backing up, so it would be this way. This is also why whenever you slam on the brakes, you go forward because your body wants to continue going forward. The seatbelt, hopefully, that you're wearing stops you and pushes you back. So it will not be going backwards unless you were backing up. And it would not stay stationary because it's not bolted to the car. And the last one is that it would go straight up. Makes no sense whatsoever. So the correct answer is A. Okay, number 16. Jack placed a coin on a card on top of a glass. He quickly pushed the card and the coin fell into the cup. So just, we did this one in our inertia lab. And this little penny right here is at rest. And it will continue to stay at rest until we apply an unbalanced force. That's our little flick. And then the unbalanced force of gravity will then pull it down here. So how does this force is equal to mass times acceleration? Well, this is a great formula, but that's Newton's second law. This is more about its inertia. A body in motion stays in motion, or a body at rest tends to stay at rest unless acted upon by an outside force. I like this one. Momentum equals mass times velocity. We actually don't even talk about momentum, and it's like the strength of something. So not that. For every action, there's an equal and opposite reaction. That's Newton's third law, and this is more about it's his law of inertia. Number 17, a race car accelerates at a rate of 19 meters per second each second. So that's basically saying acceleration is 19 meters per second squared. Meters per second each second per second squared. If the mass of the race car is 16 kilograms, determine the net force. So we are going to put this into the triangle again. We are looking for force, so we just plug this in. My mass, actually that's 1600, is 1600. It's side by side, so we just need to multiply this, and the correct answer is 30,400. Thank you, Mrs. Martinez, for not making me do all this. 30,400 newtons. So all of these are wrong. Number 18, according to the above graph, what is the average speed of the car after 3 seconds? So we have 3 seconds right here. And so average speed after that time, speed is distance divided by time, and his distance that he went is going to be 15 meters in the amount of 3 seconds. So 15 divided by 3 is going to be 5 meters per second. Number 19, what is the speed of the object represented by the graph? Again, in order to do speed, we take the distance divided by the time. Now this is a straight line. So a straight line on a distance versus time graph means that it is a constant speed. So that means that no matter where on this line, it should all be the same speed. So I like to choose one that's nice and easy. This one right here at 50, it would be my distance, 50 meters, divided by the total time right here, 10 seconds. 50 divided by 10 is 5 meters per second. C. Okay, number 20. So we've got a distance versus time graph, and again, we always look at this first. So, and this is Kara's Saturday bike trip. So we're looking for the slowest segment of Kara's trip. So, and really we're looking at right here. So this is where she's at rest. The speed where she's traveling right here is 0 meters per second, which is a speed, so this would be the slowest. This would be the next slowest right in here, and then the next slowest over here, and then the fastest right here. So, but this one right here, when they're at rest, would be the slowest. So the correct answer is G. Number 21, a student runs 2 times around a running path at a local park. Each lap is 3 kilometers, so basically times 2, so 6 kilometers. The student completes the first lap in 20 minutes. So first lap in 20 minutes. The student then sits on a bench and rests for 5 minutes. Rests 5 minutes before completing the second lap in 25 minutes. So second lap is going to be 25 minutes, so this one's going to be a little bit slower. All right. So we know it's not A because this straight line right here shows that it's a constant speed, and they did not go constant speed. For B, we do have this going right here, but we don't have where's the at-rest part. The at-rest should be a straight line, and it is missing, so not B. For C, we've got here, it looks like for 5 minutes, we're moving at a constant speed. We rest here for about 5 minutes and we continue to go. It looks at the same speed here. So these lines are basically exactly the same. We come over here, and this one is a little bit, oh no, this one right here is showing 10 minutes of rest. So this one actually is it. This one's showing 5 minutes of rest, and I guess they're just so small we really can't see that so much. So the correct answer here is going to be C.